I put a little note on the exam, a note about what conversion factors to use. I don't want you guys Googling conversion factors, odd ones that are one-offs. You know, use the standard conversion factors that I've mentioned. The same goes for nomenclature. You know, for nomenclature, I want you guys to name them using the rules that we talked about in class, you know, not some other system. And so those are the two things I wanted to say about the exam, but we'll continue what we're talking about chapter 7. Let's take a look at some more of these chapter 7 problems and go through the rest of the homework. Well, actually, the real homework is to make sure you understand everything, you know. So before the first exam, if this were an in-class exam, you know, your homework was to make sure you understand everything that was presented in class. I mean, if you're confused, then your homework is to get unconfused, you know, to make sure you clear things up. And so not working specific problems, but just make sure that all the concepts and all the problems that we do in class are well understood. And that way, if something like that comes up on a test, then you're well prepared to answer that. And if something more difficult comes up, hopefully you've had enough time to build those, what I call the neural connections, you know, between bits and pieces of information, so you can interrelate things much more easily. All right, part of that is to look at all the variety of ways, you know, that the book asks you questions, you know, to test you on the material. So here we did this problem yesterday, 37, we left off. So let's take a look at the 38. Well, let's see what they did for 37 here. So they started off with an atom and then converted it into moles. So number of atoms to moles, using Avogadro's number, and then moles to grams using the molar mass, and then grams to troy ounces using this. This is a one-off conversion factor you've gotten. So this one's okay. But if it were regular ounces, I'd expect you to be able to link together, you know, standard conversion factors like we did yesterday in determining how to convert ounces into grams. And then troy ounces to dollars, which is given here. So, how many carbon atoms has a gentleman given his bride to be if the engagement ring has a 0.500 carat diamond? All right, so we know that they're 0.500 carats, or half a carat, to 3 sig figs. And so let's see what we got here. And so we need something to get rid of carats, you know. This is carats of diamond. And so if we want to be specific, we can say carats of diamond here. So we either need something that gets rid of carats of diamond or just carats alone. Well, in the next entry here, there are 200 milligrams per carat. So 200 milligrams, I think this would be only for diamonds, but I'm not sure. But just to be on the safe side, we'll do it like this. And so carats of diamond canceled out carats of diamond, gives me milligrams of diamond. The price of diamonds doesn't seem so high when figured at dollars per atom. So how many carbon atoms are in this 0.500 carat diamond? Okay, so what we're going to do is we're going to do a specific, like for example, we can figure out how many carbon-12 atoms there are, you know, or whatever we want. And so what we'll do is we're going to go from milligrams or milligrams of diamond. So in this case, we'll just go from milligrams to grams. There are 1,000 milligrams per 1 gram. This is valid for anything. And so now we have grams of diamond. Well, diamond is just pure carbon. And so for carbon, there is 1 mole of carbon atoms per 12.01 grams of carbon atoms. These are average carbon atoms. So this gives us the moles of average carbon atoms here. Okay. And then they want the number, how many carbon atoms. Okay, so then the grams of carbon, diamond and carbon are the same thing. And so that's why I can cancel out carbon with diamond. Once we get moles of carbon, we can figure out the number by using Avogadro's number, 6.022 times 10 to the 23rd, carbon atoms, average, divided by 1 mole of carbon atoms. And so moles of carbon atoms cancel. And so what we end up with are just the number of carbon atoms here. And so we can just punch that out from the calculator and see what we get. Look at 0.5 times 200 divided by 1,000 divided by 12.01 times 6.022 times 10 to the 23rd. This gives us 5.014 times 10 to the 21, carbon atoms. 10 to the 21, we could break that down. We'll go with a trillion at 10 to the 12 is a trillion. It's a trillion. And then we need 9 more, so that's a billion. A billion. So if we take a billion and a trillion, put them together, we'll make 10 to the 21. So this is 5 billion trillion carbon atoms. It's a lot of carbon atoms in that diamond. Now, out of that 5 billion trillion carbon atoms, we have 2 isotopes. And so this will be an extra. This would be like an advanced problem, But advanced problems, like I said, are much easier to do if you have the basics mastered. And so if we know we have 5 billion trillion carbon atoms, then we can look, 99.85% of those are carbon-12. We can look this up in the book, or 98. Is it 98.115? No. Actually, I better look it up in the book. We can figure out what the natural abundance of carbon-12 is and the natural abundance of carbon-13 is. And I'm going to do that just by going to our table that we used in the PowerPoint from our book. So this was in the previous chapter, or 2 chapters ago, chapter 5. So let me go there. Okay. Well, carbon-12 is 98.93. And carbon-13 is 1.07, 1.07. All right, so remember that. So 1.07%, carbon has 2 natural isotopes. And so this is just a follow-up question on this particular problem. And so an advanced problem would be, how many carbon-12 atoms do we have and how many carbon-13 atoms do we have? And so carbon consists of, naturally occurring carbon consists of 2 isotopes, carbon-12 and carbon-13. Carbon-13 is 1.07% and the rest is carbon-12. So that's going to be 98.93%. These 2 add up to 100%. Carbon-14 is negligible, or extremely small. And so for these 2 isotopes, well, how many carbon-12s? Well, how many carbon-12s, we would just add on. So let's say we have 5. We're actually allowed 3 sig figs here, unless you It depends. This is probably exact. And so it looks like we are allowed 3 sig figs. So we'll just call it 5.01 sub 4 times 10 to the 21 carbon atoms. And so out of all these carbon atoms, we multiply it by the percentage. 98.93 out of 100 will be carbon 12. And so 98.93 carbon 12 atoms for every 100 carbon atoms. Okay, and so this is going to give us the number of carbon 12 atoms in this diamond here. And those weigh exactly 12 AMU by definition. Now, if we want to figure out the number of carbon 13, the rest would be carbon 13, or we could just do it using dimensional analysis. Using dimensional analysis, it's going to be 5.014 times 10 to the 21 carbon atoms times 1.07 carbon 13 atoms for every 100 carbon atoms. Now, this is an atom ratio here. We could also do a mole ratio. So other options are to do mole ratio. These are the variations that you see when you do a lot of problems. When you do a lot of problems or look at a lot of problems, you see lots of ways of doing different things, the same, to get the same answer. And so other options is to use a mole ratio. So for example, what we could say is we could say 98.93 moles of carbon 12 atoms for every 100 moles of carbon atoms. And so mole ratio, is the same as the atom ratio here, etc. We could do, for carbon 13, it would be 1.07 moles of carbon 13 per 100 moles of carbon atoms. And then we could insert that here, here instead. And so there are different ways we could do it. And then if we did that, then we'd say 6.022 times 10 to the 23rd carbon, let's say 13 atoms per mole carbon 13 atoms. And so those are the types of things we can do. So that would be a small variation on this to make it an advanced problem, let's say. All right, let's move on here. This. All right, next question here. Calculate the percentage composition by mass of each compound. So we'll do, let's say, let me talk about ammonium nitrate, because ammonium nitrate is often screwed up. And so the first thing is, what is the formula for ammonium nitrate? And so let's do that. The formula for ammonium nitrate, ammonium ions are NH4 plus, nitrate is NO3 minus. And so the formula is NH4 NO3. Now, when we do the percentage, so for example, if we do percentage of nitrogen, then we need to know the mass of nitrogen over the total mass times 100%. And so this gives you the percent nitrogen by mass. This is not the percent nitrogen by atom. If we did the percent nitrogen by atom, we have 1 plus 4 is 5, plus 1 is 6, plus 3 is 9. Okay, 2 out of the 9 atoms is nitrogen, 4 out of the 9 atoms is hydrogen, and 3 out of the 9 atoms is oxygen. And so then we can calculate, we multiply that, 2/9 times 100%, percent nitrogen by atom, etc. All right, so what is the mass of nitrogen? Now we have 2 nitrogens, if we have 2 nitrogens, it's 2 times 1401. So we got 2 times 1401. Now the units are either going to be in grams or U, so I'm going to leave off the units just as long as we have the same units in the numerator and the denominator over the total. Now, what is the total mass? So we have 2 nitrogens at 2802 after I multiply. Then I have 4 hydrogens. 4 times 101 is 404. Then I have 3 oxygens. 3 times 16 is 4800. And so it comes out to 6, 0, 16, 20, and 8, 8006. And so the total mass of ammonium nitrate is 80.06 grams or U. You know, it depends if you're looking at per formula unit. You know, this doesn't form molecules. Even though this is all nonmetals, this is not molecular. This is one of the exceptions to the rule. This is ionic, even though it's all nonmetals. And that's because it consists of the ammonium ion and the nitrate ion. Here. And then we'll go times 100%. That should give us the percent nitrogen by mass. So that's going to be 28.02 divided by 8006 times 100%, 34.99%. 34.99%. So if I had a 99, let's see, I'm allowed actually 4 sig figs. So if I'm allowed 4 sig figs, I'm going to carry 1 extra at 8. And so it's about 35%. So if I had 100 grams of ammonium nitrate, in that 100 grams of ammonium nitrate, I will have 35 grams worth of nitrogen atoms. That's one way of thinking about it. All right, we do the same thing, you know, for percent hydrogen. The percent hydrogen, we have 404 out of 80. 404 out of 80.06 times 100%. And so what's that going to give us? 404 divided by 80.06 times 100 is going to be 5. 5, we're allowed 4 sig figs, 5.0462, 5.046, and carry extra 2% hydrogen. This percent nitrogen, percent hydrogen. These are all by mass. We usually say by mass here. Or sometimes we just say M over M. This is M over M percent. Percentages aren't always by mass. This is M over M is the mass of component A over total mass. We have a V over V, volume percent, you know, so we have volume of component A over total volume. Sometimes we have a mix, a mass over V. Mass of component A, you know, a mixture is going to consist of different components. There's a mixture of atoms or a compound. Actually, it's not a mixture because the composition is fixed, but in a sense it is. In that sense, as well, component A or atom A over the B. We do percentages for everything: mixtures, pure compounds, whatever. You know, diamond's 100% carbon, so it's fine, etc. So when we say by mass, that's an M over M. You know, mass of component A, which is nitrogen, over the total mass. Here. Okay, this is called the fraction. And so we take the mass fraction, the volume fraction, the mass over volume fraction, and then convert it to a percent. The way we convert it to a percentage is by taking the fraction and multiplying it by 100%. So that's the percent. The percent oxygen is the remainder. So what we can do is we can add these two up and subtract that from 100%, and then we'll get it. And so one way we can get the percent oxygen is equal to 100% minus the percent nitrogen minus the percent hydrogen. That's one way we can do it. Or we could calculate it, you know, we could calculate it at 48.00 over the total of 80.06. But it'll be quicker for maybe to just do the 100, because all three have to add up to 100%. So it's 100 minus 34.998 minus 5.0462. That gives me, oops, what did I do? Screw that up. Let me fix that. 59.955%. So this is 59.955%. I'll carry an extra digit there. Just to do that. If I did it this way, just calculating it, I should get the same answer within round off error. So let me go ahead and calculate it. It's going to be 48 U or grams of oxygen atoms. This is not O2, right? Divided by 80.06 total U or grams times 100. 59 point, okay, so if I went ahead and calculated, I got 59.955%. I got the same number, but sometimes you don't get the same number because of how you round these. If you round these prematurely, you won't get the same number. Well, let's see what the book got here for this. And so they did the nitrogen first. They rounded it to 35. That's okay. The hydrogen, they used more precise here. What did I use? I should have used, because this one I screwed up. I should have used 1008 in this case, because if I use 101, I don't get 4 sig figs in hydrogen. And so they did it correctly. I did it incorrectly, because now I have only 3 sig figs, and I want 4 sig figs in all my answers. And so in this particular instance, I should have used 1008 on the top. I could have used 404 here, 101, because it's decimal places. When you do addition, it's dictated by how many decimal places, and this would end up in 4 sig figs, even though I only have 3 sig figs here. And so in compounds, I use 101 for hydrogen. When hydrogen's alone here, like in the numerator, I should use 1008, and I should have used 1008. And so that was my mistake there. And they got 5037, I got 5046, okay, due to rounding. I did too much rounding, right? They didn't do too much rounding. Oxygen is the same, but they rounded the answer here. This worked out to add up to 100%. Yeah. Okay. All right, so let's take a look at the others. The others are going to be quite similar. So aluminum sulfate, we just look, okay, you get the formula: 2 aluminums, 3 sulfurs, 12 oxygens, you know. And so if we do aluminum, you know, it's 2 aluminums. They're doing it by grams. We could do it by U, it doesn't matter. That's the same number numerically because of the way the mole is defined. Divided by the total mass. The total mass they didn't show the calculation for, but you would have done it here. And so it's the same kind of setup. 2 aluminums, 3 sulfurs, 12 oxygens. This is a check to make sure it adds up to 100%. Ammonium carbonate. Here. So formula: 2 nitrogens, 8 hydrogens, 1 carbon, 3 oxygens. 2 nitrogens over the total 2802. 8 hydrogens. Here again, the hydrogens, they use the 4 sig figs here, which is good. As in the numerator, it's only hydrogen alone. In the denominator, it's hydrogen in the compound. Now this hydrogen alone, these are hydrogen atoms because all these hydrogens are locked in this compound. It's not H2 gas here. And so that's the percent of hydrogen atoms, percent of the carbon, percent of the oxygen. And so we just got to make sure we get the numbers right. And these masses just come from the... And so one part of this is making sure you get the right formula. If you don't get the right formula, obviously your percentages are going to be totally off. And then also making sure you have the numbers right, you know. Manganese 4 sulfide, MnS2, you know, 1 manganese, 2 sulfurs. Okay, so this is just extra practice for nomenclature, and we could do these as well, but if you feel comfortable with those, just in nomenclature, you can move on here. Magnesium nitrate, MgNO3, et cetera, et cetera. Lithium fluoride is used as a flux when welding or soldering aluminum. How many grams of lithium are in 1.00 pounds? 454 grams. I don't give you this, and I want you to know this to 4 sig figs of lithium fluoride. And so the first thing is, what is the formula for lithium fluoride? And so if you can't get that, then you can't answer this question. And you might think, well, do I really need to know that? Because this is what we have here is take-home exam. You're going to need to know these, you know, at least have pretty good recall for these, you know, as you go on. If you can't do simple nomenclature like this, then you're going to be in very serious trouble further down the road. Okay, so now's the time to memorize it. Now, how do you memorize things? I usually memorize things by writing it over and over again. So chromate, you know, CrO42 minus, CrO42 minus. Just write it over and over again, you know, 50 times, 100 times, you know, 200 times, until you're sick of it. And when you're sick of it, then you know it. Same thing with dichromate, you know, etc. So lithium fluoride, how many grams of lithium are 1 pound of lithium fluoride? So what we have is this is just dimensional analysis. We have 1 pound of LiF, pure lithium fluoride, solid, it's pure salt. And then we want to get rid of pounds or pounds of lithium fluoride. Well, it looks like we can only get rid of pounds. So we can get rid of pounds by going to grams, 453.6 grams. I want you to know this one. Why? Because it has 4 sig figs. I don't want you to know this one because it has 3 sig figs. I don't know why the book is inconsistent. You know, for hydrogen, yes, they use 1.008, but for grams to pounds, they don't use 454. Why for hydrogen they use 4 sig figs and this they only use 3 sig figs? It makes no sense to me. So we use 4 sig figs. We want 4 sig figs. All right, so this is going to convert pounds to grams of lithium fluoride. So once we have grams of lithium fluoride, then we want to get rid of grams. So we can get rid of grams and go to kilograms or milligrams or whatever, but those aren't going to take us anywhere. But we could get rid of grams of lithium fluoride and convert that to moles of lithium fluoride. You know, this is a molar. This is a gram to mole conversion. Gram to mole conversion is very common. And so we need the mass of lithium, which I think was 6.94. Fluorine's 1900. Lithium, what is the average mass of a lithium atom? Now, we can look at the periodic table. So let's do that. Oh, I didn't want the Fisher one. Hopefully that gives us. They just keep asking to buy it. So hopefully this has a decent resolution. A good periodic table is good to have, you know, handy. I have a periodic table app on my phone. They're free. You can get it too. Hopefully this one doesn't give me a whole bunch of other junk. We could just look up the average mass of lithium. I can't read it. Well, I need to keep a periodic table handy on my computer, and I do have one. Let me just use mine. I have a PDF of periodic table. Search the right folder. Well, I had a PDF of the periodic table. I must have done some house cleaning and gotten rid of it. Let's see. Hopefully this one doesn't give me a whole bunch of advertising. .94 out of these. Find a decent periodic table. So Lithium is 6.94. So lithium consists of lithium 6 and lithium 7. Which one is more abundant, lithium 6 or lithium 7? Tell me. Is everybody working on the exam? That's a fatal mistake some students make. In easier classes, it's okay, but the fatal mistake is that is not going to class, you know, because well, you guys, I guess I don't have to tell you guys. I should be telling the people not coming to class because they don't know which stuff is most important. I guess it's not that fatal because there's recordings, and so maybe they're watching the recordings. Canvas, Carlos, you turn it in on Canvas. Link is already up. Okay. As a PDF, preferably. Okay, so yeah, let's see, Kazra, that's, did you say 6 is more common? Okay. 6 is not more common. It's 7 that's more common. You know how I could tell? I could tell is that there are 2. And so what does the average lithium weigh? The average lithium weighs 6.97. If the average lithium atom weighs 6.97, well, 6.97 is very close to 7. You know, and this is a mass number. This is not the mass, but the mass number is close to the mass. You know, it's not exactly the mass, but it's close. And so if the average weighs close to 7, then that means there's very little lithium 6. Likewise, let's say if the average of lithium, let's say the average was 6.01, then it's mostly lithium 6. There's very little lithium 7. That's, yeah, okay, good. That's how you can tell. It's like, you know, carbon 12 and carbon 13. You know, the average is 12.01, which is very close to carbon 12. Well, that makes sense. It's 99% carbon 12. It's only 1% carbon 13. Okay, so going here, what is the molar mass? The molar mass is going to be 9, is it 9.7 or 9.4? 6.94. 25, 25.94. So 25.94. So we can convert grams of lithium fluoride to moles of lithium fluoride. Once we have moles of lithium fluoride, they're asking how many grams of lithium are in here. And so that's how many, this is what I do. You know, even though this is long, I do it this way. And the reason I do it this way is there are other ways I can do it. I'm going to show you one more way, and that's going to be the book's way. Then once I have that, then I go, there's 1 mole of lithium atoms for every 1 mole of lithium fluoride formula units. And the moles of lithium fluoride cancels out. Then I know what the average mass of lithium atoms are, and that is there's 6.94 grams of lithium for every mole of lithium atoms. Okay. And so now the moles of lithium cancels out the moles of lithium and gives me grams of lithium. So this tells me how many grams of lithium I have once I do the calculation. Now the other way I could do that is I could calculate the percent by mass, you know, of lithium in this. And so the percent by mass, well, there are 2 ways. I don't have to do percent by mass. I could just do the mass ratio. And so one way is doing the mass ratio. If I use the mass ratio, then it's 6.94 grams of lithium for every 25.94 grams of lithium fluoride. Or that's a mass ratio. Or I could use the percent by mass. Percent by mass means that I'll take the mass ratio and multiply it by 100%. So 6.94 over 25.94 times 100% gives me what percent by mass? And so let's do that. 6.94 divided by 25.94 times 100 gives me 26.75%. So I get 26.75. I'm only allowed 3 sig figs because of that, unfortunately. But this is 26.75% lithium. And therefore, I can use this conversion factor, 26.75 grams of lithium for every 100 grams of lithium fluoride. So I could use these say the same thing. The mass ratio is the same as this fractional ratio here. You know, this is just normalized to 100, part per 100. This is parts per whatever total we have here. And so I could use either of these two as a conversion factor here. So when I get to grams of lithium fluoride, I can go straight to grams of lithium. You might say, hey, that saves me 2 steps, you know? But yeah, it saves you 2 steps, but you have to do an extra calculation here, which I don't like to do. I like to use just the standard, the minimum number of conversion factors, and just string them along. So let's see what the book did. And if the book, I'm sure the book used percent by mass or the mass ratio. Okay, the book used the mass ratio here. You might go, wow, why didn't I? You know, you could have used the mass ratio here, or the percent by mass ratio, or just string it along like this. If you string along like this is your standard stoichiometry problem here, stringing along a whole bunch of conversion factors. So when we look at this, this is standard stoichiometry in the sense that we're going here. Well, let's take a look at this, analyze this. So we're doing a gram to mole conversion. So we're going from grams of lithium fluoride to moles of lithium fluoride. And then a mole to mole conversion. So we're going from moles of lithium fluoride to moles of lithium. And then a mole to gram conversion. We're going from moles of lithium to grams of lithium. And so this is called a stoichiometry map. Here. This is a very common pattern here in stoichiometry maps, right here. And so I'm just doing it in a common method here. Calculating the mass ratio, although it's easy, you know, I don't even really bother doing it. I do it this way. You do it whatever way you want. It's fun. Okay, let's continue on here. All right, next, I'm just going to do the ones with the problems here just to show you, you know, this is the approach I take. You know, if the answers are given for all problems, I do all problems. But here, the answer is only given for the odd number of problems. So I'm just going to do the odd ones because that's going to, usually the even ones would be a sister problem. So if I wanted to try it again, I'd try that, but I don't have the answer for it. But anyway, if you master the odd, then the even should be easy. Potassium sulfate is found in some fertilizers as a source of potassium. How many grams of potassium can be obtained from 57.4 grams of the compound? So what is potassium sulfate? That's the first thing we need. And so potassium sulfate is, well, sulfate's SO4 2 minus. Potassium is K plus, so we need 2 potassiums to balance out the charge, so it's K2SO4. All right, so if we have 57.4 grams of K2SO4, maybe the way the book does it, if you have a lot of these, maybe the way the book does it is the best way. But, you know, on our standard stoichiometry, we're going to go from grams of this to moles of that. Okay. And so this would be our standard stoichiometry here. And so potassium, we have to get the molar mass of the potassium and sulfate. Since I'm familiar with that, I don't want to waste time calculating molar masses if I'm already good. If I'm not good at calculating molar masses, then I won't do it. But in this particular case, I'm just going to use theirs. 174.26. Again, look, they're just taking the mass ratio here. We could do that too, but I'm not. So 124.26 was it? 174.26. 174.26. So this is a very common pattern. So we're going to go grams to moles. So 174.26 grams of K2SO4 because I don't want to spend the time calculating the molar mass. We could look these up on Wikipedia as well. Per mole K2SO4. Okay, then what I do is this. I say that for every 1 mole of K2SO4, how many moles of potassium do we have? We have 2 moles of potassium, K, potassium ions, to be more specific, but we'll just write it as K potassiums. And then we go to the molar mass of potassium. The molar mass of potassium is 39.1, I think. Look what the molar mass of potassium is. 39.10. Okay, then I go to the molar mass of potassium here, which is 39.10 grams of potassium for every mole of potassium. Now this mole-to-mole conversion factor came from the chemical formula here, because the chemical formula is the atom ratio or the mole ratio. And so we could say 2 potassium atoms for every 1 K2SO4 formula unit, or we could say 2 moles of potassium ions for every 1 mole of K2SO4 formula units. You know, I should write atoms here and then formula units there, or ions, you know, potassiums are the ions, K+. But we can leave it like this. And so what we're doing is we're doing a gram to mole, and then a mole to mole, you know, conversion, as long as we know the mole ratios, and then a mole to gram conversion here. This is the way I do it here. And so that's going to give you the grams of potassium here. Now, when you look at the numbers here, they're going to be the same. It's going to be this 57.4 times 2 times 39.1 divided by 174.26. And so when we look at their setup here, that's probably much what they're going to have. 57.4 times 2 times 39.16 divided by 174.26. Right? We combined everything. The mass ratio here. I spread it out. Okay, let's move on. 49. Zinc cyanide, you know, cyanide CN minus, you should know that. This is one of the ones I want you to memorize. This is an IDE that's not monatomic. Most IDEs we get off the periodic table. Chloride, bromide, iodide, sulfide, oxide, you know, periodic table. Cyanide we don't, hydroxide we don't. Is the compound used in zinc electroplating? How many grams of the compound must be dissolved in a test bath in a laboratory to introduce 146 grams of zinc into the solution? Okay, so we have 146 grams of zinc that we want. Okay. And so in this case, we're given 146 grams of zinc. And then we want to know how many grams of the compound. The compound is zinc cyanide. And so we want how many grams of zinc cyanide we need. And so this is what I would do, you know, myself. Okay, this kind of strategy. I'm going to go from grams of zinc to moles of zinc using the molar mass, inverted. And then I'm going to go from moles of zinc to moles of zinc cyanide, because I know that for every zinc cyanide is CN2. Cyanide is -1. Zinc's fixed charge. Remember, zinc is fixed charge at 2+. And so this is ZnCN2. Okay, what is the ratio here? The mole ratio, this one is going to be 1 over the molar mass. You know, just flip over the molar mass. Zinc. This one is going to be here. For every 1 mole of zinc cyanide, we have 1 mole of zinc. 2 moles of cyanide, 1 mole of zinc. So it's just 1 to 1. And then from moles of zinc cyanide to grams of zinc cyanide using the molar mass here. And so I just use the molar mass here. This is the way I'd say it. Your book is going to probably use mass ratio again. Let's see how your book does it. Yeah, they use a mass ratio here. Mass ratio, this is the total grams of compound. This is the grams of zinc. So you use a mass ratio. Mass ratio seems, you know, more attractive because it's fewer steps. Again. Molybdenum is an element used in making steel alloys. It primarily comes from an ore called molybdenite. Molybdenite, some things are kind of tricky, you know. MOS2, you know, is that, how would you name that? You know, sometimes things become tricky, you know. And so, what mass of pure molybdenite must be treated to obtain 201 kilograms of molybdenum? All right. So, what I'm gonna take a brief foray into nomenclature and talk about some issues with nomenclature. You know, these nomenclature rules are rules, and rules aren't always perfect, right? You know, it'd be nice if you had a perfect set of rules that worked for everything, but oftentimes you don't have a perfect set of rules and it doesn't work for everything. Do you know what fool's gold is? Fool's gold is FeS2. FeS2, let me make that a subscript. FeS2. Oh, by the way, did you guys catch my error? Make sure you catch my error. 14. With number 8. I don't know if you keep an eye on Piazza. This is wrong. Sorry, it's the wrong test. Number 8 on Piazza. Fool's gold, FeS2. This is a fool's gold. What's the normal charge on sulfur? The normal charge on sulfur is 2-. But then there comes a problem with this here. This is S2-, this is S2-. That means iron must be what? Yeah, this is called pyrite. That's correct. It's fool's gold. Yeah, iron must be 4+. Well, this is wrong. Iron is not 4+. This is wrong. What this is it's an iron 2+, with an S2 2- anion. S2 2- anion is called disulfide, and it's similar to peroxide, disulfide ion. And so it's actually iron 2 disulfide or just iron disulfide. And so oftentimes this is called iron disulfide because the nomenclature system failed in this. Do you know what magnetite is? Let's do another one here. Erase this. I'm going to type it here. Don't worry about this for the test. I'm just talking about this because the nomenclature rules aren't always perfect. Magnetite is Fe2O. Fe2O3. No, it's not Fe2. It's Fe2O4. It's magnetite. So what does that mean? For the charges on this. If we look at magnetite, magnetite, well, what's oxygen's typical charge? Oxygen is -2. We'll do that. And so I have 4 of them. So 1, 2, 3, 4. So altogether, the negative charge is -8. I have Fe3, sorry, Fe3O4. Let me change that. Magnetite is Fe3O4. And this has to be +8 because magnetite is a neutral compound, so +8. And so that means each of these is +8 thirds. It's +8 thirds. +8 thirds is 2 1/3. No, 2 2/3. That equals +2 2/3. So this has got to be +2 2/3. And this has got to be +2 2/3. So if I take 3 times 2 2/3 or 3 times 8/3, that'll give me +8. And so how should I call this then? Do I call this iron, Roman numeral 2 2/3 oxide? Is that correct? So think about it for a moment and tell me what I should call it. I'll be right back. No, this is wrong here. Yeah, Vanessa, you're right. It's a mix. And so really, this is a mix. What we have here is we have 2 iron 3s and 1 iron 2. And so how do we name that? You know, how do we name that? And so this is a problem sometimes that comes up. So one option is to name it like naming binary molecular compounds. Even though this is an ionic compound, we would name this tri-iron tetroxide. Okay, then it's easy. We have 3 irons and 4 oxygens. So this is the easier system here. Or we'd have to name it by ion. You know, it would be di-iron 3, mono iron 2, you know. We see this is the same problem. These are called mixed. This is a mixed cation salt. We also have mixed anion salts. Same problem here. If we're looking at this one, what would we call this? Na2KPO4. You know, if you call this sodium potassium phosphate, we don't know how many sodiums there are. So in this case, we'd have to call it disodium potassium phosphate or disodium monopotassium phosphate. And so, you know, these are rules, and rules, there are some places where, you know, you have to break the rule, otherwise it doesn't make sense sometimes, you know. Okay, so this is just a side topic here. Well, the same thing's going to happen with this. If we tried to name this using our rules, we're going to run into a little bit of a problem. Because molybdenite is not S sulfide, it's disulfide. And so this is actually molybdenum with a +2 charge, not molybdenum with a +4 charge. But it's okay, we can just call it molybdenite instead. And so is an element used, it primarily comes from an ore, this ore. What mass of pure molybdenite must be treated to obtain 201 kilograms of molybdenum? And so this is the way I would do it. Just, you know, mental map here, and then you can go through these quickly and see how they compare it to the way they do it. They start off with kilograms of molybdenum, then I would go to grams of molybdenum, and then from grams of molybdenum I'd go to moles of molybdenum using the you know, molar mass flipped over upside down, and then from moles of molybdenum I go to moles of MOS2. And then from moles of MOS2, I'd go to grams of MOS2. And so I need the molar mass of molybdenum. I need the mole ratio here. The mole ratio is for every mole of MO, I have 1 mole of MOS2. And then the grams. Okay, again, they're going to use the mass ratio, but I don't use the mass ratio because I just solve problems kind of the same way. So they use a mass ratio, which is fine. You use mass ratio. How many grams of insecticide calcium chlorate must be measured if a sample did contain 4.17 grams of chlorine? So calcium chlorate has chlorine present in there. So what is calcium chlorate? Well, let's take a look. Chlorate, you should know. This should be automatic. Look at the periodic table and you should get that immediately. Calcium is 2+. So calcium chlorate is CaClO2, 3, like that. And we need 2 of them. All right, so we want 4.17 grams of just pure chlorine. So 4.17 grams of Cl. Okay. Then what I do here is I'll go to moles of Cl. And then from moles of Cl, I'll go to moles of CaClO3. Because all the chlorine is going to come from CaClO3 too. Now, what is the mole ratio that I'm going to use? In this step, the mole ratio is I'm going to have 2 moles of chlorine. You know, I can see there's going to be 2 moles of chlorine for every 1 mole of CaClO3 too. But I have to flip it upside down. And so I'm going to have to flip this upside down so that the CaClO3 2 is on top and the 2 moles of Cl are on the bottom. And so that's going to convert chlorine into CaClO3 and then just go to grams of insecticide, which is the CaClO3 2. Okay. And there I have to calculate the molar mass. All right, and again, your book is going to use the mass ratio. Okay. Numbers are going to come out the same, though. So a bunch of mass ratio type problems. Explain why C6H10 must be a molecular formula. C6H10, whereas C7H10 could be molecular and empirical or both. Okay, C6H10 has to be molecular because it's empirical is the simplest ratio, and so we could reduce this more. The empirical formula for this is going to be C3H5 divided by 2. Yeah, and so we can divide it by 2. C3H5, and then we can't reduce that further. C7H10 we can't reduce because 7. Yeah. And so C7H10 is an empirical formula. It's possible that this is a molecular formula if the molecule weighs this much, or it might be some ratio of this. It might be 2 double it or triple it. So it might be C14H20, it's a molecule. Molecules can get very, very big, and so we could weigh individual molecules using the mass spectrometer. A certain compound is 52.2% carbon, 13.0% hydrogen, and 34.8% oxygen. Find the empirical formula. And so what we do here is we assume a 100-gram sample. I did an example of this. And so we're just mentally going through. So there's 52.2 grams of carbon. Convert that into moles of carbon. 13 grams of hydrogen, convert it into moles, and 34.8 grams of oxygen, convert it to moles, and then get the simplest mole ratio. That's the formula. And so here, they took the grams, assuming a 100-gram sample, converted to moles, and then get the simplest mole ratio, which is a 2. The simplest mole ratio is dividing by the smallest. So we divide by the smallest. 2.18 divided by 2.18 gives us 1.00. 12.9 divided by 2.18 gives us 5.92. 4.35 divided by 2.18 gives us 2.00. And then we'll just round it 261. So C2H60. That's the empirical formula. For the molecular formula, we need to know how much the molecule weighs. We can figure out the weight of the empirical unit here. Two carbons is 28, plus 6 for the hydrogen is 34, plus 16 for this is 50. So this weighs about 50 U. And so if the molecule weighs about 50 U, then this is it. If the molecule weighs 100 U, then it's double this. If the molecule weighs 150 U, it's triple this. A researcher exposes 11.89 grams of iron to a stream of oxygen. A researcher exposes 11.89 grams of iron to a stream of oxygen until it reacts to produce 16.99 grams of a pure oxide of iron. What is the empirical formula of the product? Okay. And so in this case, we know we have 11.89 grams of iron, and we have 16.99 grams total. So 16.99 grams total minus 11.89 grams of iron gives us the grams of oxygen. And so in this case, first we got to figure out how many grams of oxygen there are. And so we have the total, the difference between these is the grams of oxygen. So that's what they're going to do here. So in other words, 11.89 grams of iron plus 5.10 grams of oxygen is going to give us 16.99 grams total. And so once we get the grams of each element, then grams to moles, and then get the simplest mole ratio. But look at what happened here. When we do the simplest mole ratio, we divide by the smallest. So 0.213 divided by 0.213 gives us 1. However, when we do 3.319 divided by 0.213 gives us 1.5. Should I round 1.5 to 2? No. Or should I round down 1.5 to 1? No. This is kind of stuck in the middle. So the best thing is to double this. If I double this, I get 2 and 3. And so it's Fe2O3. And that's the simplest. Whereas in the previous example, it was close enough. 592 is close enough to 6, so we'll round it to 6. But 1.5 is not close enough to 2 to round it to 2. It's stuck right in the middle. And that leads to a huge round-off error. So it's easier to double it here. And so that's what they did here. So that's a variation of what happened here. All right, I went a little over. I wasn't keeping track of time. And so what we're going to do is we'll take another break. Yeah, it's break time, Ezra. Sorry. Go off mic. I mean, go off mute and remind me if it's break time, because sometimes I don't see the chat. So let's go ahead and take a break. We'll take a break for 15 minutes. And so we'll be back at 52. Okay. So I'll see you guys back at 52. I'm going to pause the recording. Oh, actually, okay. All right, let's take a look at the next problem here. So this was a little variation here that we see. So again, here, so we're getting the percent by mass composition. We assume 100 grams, we go grams to moles, get the mole ratio. So let's see what they did. You have the grams, you get the moles. Okay, then they divided by the smallest, 143, and they got 1, 1, and about 3. So CHF3, so standard type problem. Let's take a look. Next one. An antifreeze and coolant widely used in automobile engines is 38.7% carbon, 99.7% hydrogen, and 51.6% oxygen. Its molar mass is 62.0 grams per mole. What is the molecular formula of the compound? So far what we've been getting are the empirical formulas. So the empirical formula is the simplest ratio. And so this has a 2-6-1 ratio. 2-6-1. This is a 2-3. This is a 1-1-3. Now we don't know if it's iron and oxygen don't form molecules. So this is it. Empirical formula is the formula unit for this. There's no such thing as molecular formula for an ionic compound. But when we have a molecular compound like this, then we don't know. This is blank. This is not known. Same thing with this. And so here, we got to get the empirical formula. We'll do the empirical formula standard method here. So grams to moles, and then figure out the simplest mole ratio by dividing by the smallest here. And so we get a 1-3-1 ratio here. So C1H3O1. Now, is that the molecular formula? Well, it depends on how much this unit weighs. So if I look at the mass of this particular unit, let's figure out the mass of this. So we have one carbon atom, and a carbon atom weighs 1201 average. We have 3 hydrogen atoms, and it's 101, so it's going to be 303. And then we have 1 oxygen atom, which is going to be 1600. And so when we look at how much this unit weighs, this is the empirical mass. The empirical mass is 40, 5, 11, 31, 31.04 U or grams. U per molecule or unit, in this case is a unit, or grams per mole of units. That would be the formula unit. Now, if the actual molecule weighs that, then this is the molecular formula. But the actual molecule doesn't weigh that. The actual molecule weighs 62, not 31. And so the molecule is actually twice as heavy. So this is only half the molecule. And so if the molecule is twice as heavy, we have to double everything in order to account for that. And so doubling everything, or you could take the ratio, this is the molecular mass over the empirical mass ratio. So 62 over 31 is double, or you could just visually see that. And so we need to double it. So the molecular formula is C2H6O2. And so we need to have the molar mass or the molecular mass in order to determine it. Molar mass is grams per mole. Molecular mass is U per molecule. Okay. And it's the same number. Okay, let's continue on here. The compound is 73.1% chlorine, 24.8%, and the balance is hydrogen. The balance, it has to add up to 100%. So we could figure out how many, what the percentage of hydrogen is. 73.1 plus 24.8 is going to be 97.9. And so that means the 2.1% is hydrogen. If the molar mass of the compound is 97 grams, so first we got to figure out the empirical formula, then we can figure out the molecular formula by comparing the empirical mass with the molecular mass. But first we get the empirical formula. So we do grams to moles, each of these, using Chlorine's 35.45, carbon's 1201, and hydrogen alone is 1008. So we use that to get the moles here, the 3 sig figs. And then we can get the mole ratio here. Well, it turns out it's ClCH. Everything's 1 to 1 to 1. But when we do Cl, how much is the empirical mass for this? How much does the empirical unit weigh? And so we can determine the mass of the empirical unit. Chlorine is 35.45. That's off the periodic table. Carbon is 1201, also off the periodic table, and hydrogen is 1. Okay, this is a compound. So hydrogen alone, I'm going to use 1008. So when I go from grams to moles here, I'm going to use this conversion factor. I'm going to times this by 1 mole of H atoms. Weighs 1.008 grams. Over here, I'm just going to use 101 because I'll have the right number of sig figs, and I could have rounded it in the end. Anyway, I got to round it to 2 decimal places. So if I go 3 decimal places, that 8's going to round to 1. And so 5, 6, 7, that's going to be 7, and then 4, and then this is going to be 7, 8, and then this is 4, 48, 47. So an empirical unit of this is 48.47 U or grams. U per, unit or grams per, mole of units. I don't know if this is the molecule yet, but when we look at the actual mass is 97, so it's double this. And so we can see that here, 97 divided 49 gives us about 2, so it's double it. And so we can double everything, 2 chlorines, 2 carbons, 2 hydrogens. So similar to the last problem where it was double. It could be triple, or it could be quadruple. That happens too, but in these particular examples, it was just double. Okay, let's move on here. So these, I'm going through these ones, and what you should do is you should go through these by yourself, and then you can check your answers as well. Even though you might think it's repetitive, you want to. It's like doing drills. You do drills to get better. This type of stuff. So that's what you would end up doing. I do it, but you should do it too. The exact same problems. The term molecular mass applies mostly to ionic compounds. That's false. Ionic compounds don't form molecules. The molar mass is measured in atomic mass units. That's false. Molar mass is in grams. Molar is bringing it to macroscopic. Grams are larger than atomic mass units, yes. Therefore, molar mass is numerically larger than atomic mass. That's false. The number is the same. The number doesn't change. The molar mass of hydrogen is read directly from the periodic table. Yes. Whether it is monatomic hydrogen or hydrogen gas, no. Hydrogen gas, we have to double atomic hydrogen. Why do they call it monatomic? I don't know. It's just atomic hydrogen. You can do whatever. So we don't call it monatomic hydrogen. We just call it atomic hydrogen, or hydrogen gas, or diatomic hydrogen. Again, that's false. An empirical formula is always a molecular. That's false. Although molecular formula may or may not be an empirical formula. Empirical is not always molecular. We just saw in the last 2 examples. Would you need a truck to transport 10 to the 25th atoms of copper? No. This is just over a mole. This is about a mole is 10 to the 23rd. So this would be like 100 moles. So 100 moles, copper weighs 63 grams on average. Off the periodic table, it's 63 grams. I don't have my periodic table in front of me, but I know the number roughly. And so the 63 grams, 100 times that, because it would be 10 to the 23rd would be a mole, and so 10 squared would be 100. 100 times that would be 6,000 or 6 kilograms of copper, 6,300 grams. A kilogram, you don't need it. Kilogram is about 2 pounds. So, the stable form, well, they're using dimensional analysis. I did this just based on a mental calculation here. They're actually doing the calculation here. 10 to the 25th atoms, copper, convert atoms of copper to moles of copper, moles of copper to grams of copper, grams of copper to pounds of copper. So that's what they did here. The stable form of elemental phosphorus is a tetraatomic molecule. Calculate the number of molecules and atoms in 85.0 grams of P4. All right, now this becomes a little tricky about how we do things here, and this is often mixed up by students. And so this is the way we're going to do this one here. We have 85.0 grams of P4. And so this is 85 grams of pure phosphorus atoms here. And so even if we wrote 85.0 grams of P rather than P4, we'll get the same number of atoms. However, we won't get the same number of molecules, here. So we're going to go 85.0 grams of P4. And then we need to convert that to moles. Okay, so here's where it's going to be critical that we do P4 because, phosphorus is what? 32 point is phosphorus. And so I'm going to go and look up phosphorus. Since I'm having a struggle with finding phosphorus, a decent periodic table, I'm just going to go to phosphorus on the Wikipedia, 30.97 here. Just use that, 30.97. Okay, but one phosphorus is 30.97, but how many phosphoruses do we have? 30.97. We have 4 phosphoruses. So 4 phosphorus will be 4 times 30.97, which is going to give us, let's see, 4 times 30.97 gives us 123.88. 123.88. We're only allowed 4 sig figs, but I'll carry an extra, grams per mole or U per molecule. And so we're going to use grams. So mole of P4 molecules weighs 123.8 sub 8. I'll carry an extra grams, P4 molecules. And so this gives us the moles of P4 molecules, and then we could use Avogadro's number. There's 6.022 times 10 to the 23rd P4 molecules per mole of P4 molecules. So this answers the first question, how many P4 molecules are there? Now for the second question, we could do this. The second question is, we'll just add one more conversion factor. And the last conversion factor is there are 4 P atoms for every 1 P4 molecule. There are different ways we could do it. We could do atom ratio, or we could do mole ratio too. So we could have inserted it over here as well. And so that's it. Let's see what the book did. Here. So they took 85 grams of P4, converted to moles of P4 to molecules of P4. So that's what we did. For the second part, they did it this way, the way I did it. They went from grams of P4 to moles of P4, moles of P4 to molecules of P4, molecules of P4 to atoms of P4 using this. 4 atoms of phosphorus for every molecule of P4. Okay. Is it reasonable to set a dinner table with 1 mole of salt, sodium chloride, in a salt shaker with a capacity of 2 ounces? How about 1 mole of sugar? Okay, well, let's see, 2 ounces. Well, 1 mole of salt. Okay, 1 mole of sodium chloride is what we got. And so let's do that. How much, if I have 1 mole of sodium chloride, how big of a container do I need? And so let's go ahead and calculate that. This is a container based on not volume. This is a container based on mass. Ounces are mass. And so do that. We'll just set it up. I don't know if we need to calculate the numbers. So I'm going to go from 1 mole of NaCl. That's what we're starting with. And then I'm going to go to grams of NaCl. And then from grams of NaCl, I'm going to go to pounds of NaCl. I know this one, 453.6 grams in a pound. And then from pounds of NaCl, I'm going to go to ounces of NaCl because I know there's 16 ounces in a pound. And so those are the conversion factors I'll use. So let's look at the first part here. Let's see what they did. So they went from moles of NaCl to grams of NaCl using the molar mass. And then from grams of NaCl to pounds of NaCl using this. This is not just for NaCl, this is for anything. And then from pounds to ounces, 16 ounces in pound, they get 12 ounces there. Okay. So when they do the calculation, they get 12 ounces. Well, the capacity is only 2 ounces for this, so it's too much salt for the shaker. How about 1 mole of sugar in a sugar bowl with a capacity of 10 ounces? So we go from this same thing, moles of sugar to grams of sugar using the molar mass. So moles of sugar to grams of sugar, we got 12 carbons, 22 hydrogens, 11 oxygens. So we can calculate the molar mass. And then grams to pounds, and then pounds to ounces, and it comes out to 12 ounces. And this bowl has a capacity of 10 ounces. It's too much sugar. Too much sugar and too much salt for the containers. All right, let's go to 72. The quantitative significance of taking a deep breath varies, of course, with the individual. When one person did so, he found that he inhaled 2.95 times 10 to the 22nd molecules of a mixture of mostly nitrogen and oxygen, which we call air. Assuming this mixture has an average molar mass of 29 grams per mole, what is the apparent lung capacity in grams of air? Okay, so we're going to use this. This is a given, 29 grams per mole. That's the average. This is called the weighted average molar mass of air. Air is mostly nitrogen. We can figure out the mixture here. Let me do one more thing. Nitrogen, N2, is 28.02, 2 times 1401. Oxygen, 2 times 16 is 32.00. What's the average closer to? The average is closer to nitrogen. Therefore, we have more nitrogen than oxygen. So if we look at a number scale, it goes 28, 29, 30, 31, 32. And so I look here, if the average is 28, then it's 100% nitrogen. If the average is 30, then it's 50% nitrogen. And so the average is about 29, which means it's about 25% oxygen, 75% nitrogen. And so this is kind of a visual way of looking at the average, the weighted average. The weighted average is 32, it's 100% oxygen. And so this would be 100% nitrogen. We'll do nitrogen over here. This would be, if the average is 32, we have 0% nitrogen. If the average is in the middle, we have 32% nitrogen. So it goes 175%, 25%. If we look at oxygen, if the average is 28, then that means we have no oxygen, so it's 0%. If the average is 32, it's 100% oxygen. So this is what I see visually. And then if it's right in the middle, it's 50%. And so this would be 0 to 25%. So if we have 75% nitrogen, we have 25% oxygen. If we have 25% oxygen, we have 75%. I mean, 25% nitrogen, we have 75% oxygen. And so I see this visually when I'm looking at the weighted average here. This is the weighted average. Turns out it's not 25% oxygen. It's more like 21% oxygen. So this is just crude, but it's a quick way of determining it. I did the same thing for lithium. When I was thinking about lithium, I visualized this. Earlier when we were looking at it. Okay, so this is just dimensional analysis. So what I have is I have 2.95 times 10 to the 22nd molecules of mixture. And so I'm not going to, this is what I'm going to do. I'm just going to say we have some mixtures are important. So we have 2.95 times 10 to the 22nd molecules of air. And air is going to be a mixture of nitrogen and oxygen. So this is just molecules of air. And so how many moles of air is that? Well, you know, if we go molecules to moles, we'll need Avogadro's number. So there's 6.022 times 10 to the 23rd of anything, you know, per mole of that anything. So this would be molecules per mole of molecules. Okay, so that takes us from molecules of air to moles of molecules of air. And so once we get moles, then we can go to grams because they give us the molar mass, the average molar mass. This is 29 grams of air per mole of air. Okay, this is a weighted average based on the percentage here. We could calculate it, you know, ourselves. This would be a Chem 1A type problem. Calculate the molar mass of air given that it's a mixture, you know. We need the percentages. We do this the exact same way. You know, we'd have to know air is 21 out of 100 parts of oxygen, you know, times 32 would be the molar mass of oxygen, etc. You know, it's a Chem 1A style problem. But here, we're not going to worry about it. And so this is going to give us grams of air. So let's see what the book did. Come on. So they went from molecules of air to moles of air to grams of air. So it's a number to moles, moles to grams conversion. This is very common. This is why I do it. And, you know, it's a very common pattern. So I do it similarly each way. Assuming gasoline to be pure octane, it's not. Gasoline is a big mixture, but let's assume it's octane. This is called octane. It's a hydrocarbon containing 8 carbons. This is pure, 18 hydrogens. An automobile getting 25.0 miles per gallon would consume 5.62 times 10 to the 23rd molecules per mile. You know, that's almost a mole. Calculate the mass of this amount of fuel. So this amount of fuel, okay. The amount of fuel is 5.62 times 10 to the 23rd molecules of octane. And so let's just look at it here. 5.62 times 10 to the 23rd molecules of octane. And then they go from molecules of octane to moles of octane. Moles of octane to grams of octane using the molar mass. You know, 8 times 1201 plus 1818 gives us 114.22. This is 1.07 grams of octane. A researcher took 27.37 grams of a certain compound containing only carbon and hydrogen and completely burned it. Actually, I did this problem in class. Let's skip that. Cobalt A, sulfur B, oxygen C, dot XH2O is the general formula of a certain hydrate. So we have a lot of unknowns, A, B, C, and X. That's 4 unknowns. When 43.0 grams of the compound is heated to drive off the water, 26.1 grams of anhydrous compound is left. Further analysis shows that the percentage composition by mass of the anhydrate is 42.4% cobalt, 23.0% sulfur, and 34.6% oxygen. Find the empirical formula of A, the anhydrous compound, and B, the hydrate. Treat the anhydrous compound in water just as you would treat elements in calculating X in the form of the hydrate. All right, so the first thing is we can get the empirical formula. The empirical formula of the anhydrate is easy because we have 42.4 grams of cobalt, 23 grams of sulfur, and 34.6 grams of oxygen. So we just do grams to moles and then figure out the simplest mole ratio, and that's the formula for the anhydrate. Now the water we handle in a similar way, but let's look at this first. So they get the grams to moles and then get the simplest mole ratio by dividing by the smallest. And the smallest in this case is this 717. So 717 divided by 717 gives us 1. 719 divided by 717 is about 1, close enough. And 216 divided by 0.717 is 3. So it's a 113. So it's COSO3. Well, that's just cobalt 2 sulfite here. Now, how do we figure out how much water was in there? Well, they give us the weight of the water. How do they give us the weight of the water? They give us the mass of the water that was driven off. And so what we'll do here is this. The hydrated compound weighs 43 grams and the anhydrous weighs 26.1 grams. So the difference here, 43.0 minus 26.1 grams. 16. We got 16.9 grams of water was driven off. Well, this is mole ratio. These are mole ratios. All right, these are mole ratios. So we do the same thing. What they're saying is do the same thing. So if we have grams of water, we can just convert that to moles of water by using the molar mass of water. Molar mass of water, I know, 1 mole of water weighs 18.02 grams. So I can convert grams of water to moles of water and then insert that here as part of the mole ratio. So I can do here. But the tricky thing here is when you do that. Okay, and so let's take a look at how they did it here. So how do we handle the water? Okay, so this is what they did. They're doing a mole ratio, but now with compounds rather than with atoms. In the first step, they did mole ratio with the atoms. In the second step, they're going to do a mole ratio with the compounds. That is, okay, we know we have 26.1 grams of the cobalt sulfite, cobalt 2 sulfite here. And so look at what they're doing here. We know how many grams of cobalt 2 sulfite we have. We know how many grams of water we have. And so what's the mole ratio? Well, for every one of these, how many waters do we have? And so we convert this into moles using the molar mass of the compound. We convert the water, grams of water, into moles using the molar mass of the compound here. And so here is the mole ratio between the compounds. Then we divide by the smallest, 0.188. And so 0.188 divided by 0.188 gives us 1. And so for every cobalt 2 sulfite, we are going to have 0.938 divided by 0.188, 4.99, 5. So for every one of these cobalt 2 sulfite formula units, or moles of cobalt 2 sulfite, we have 5 moles of water. That's what we got. And so the ratio is 1 of these to anhydrous to 5 waters. And so it's a pentahydrate. It's a pentahydrate. Here they're showing the calculation for the grams of water here. And so this is a tough problem here. Clear that. That would be an example of an advanced problem. Okay, and now we're done with that. And so you should review those, review your notes and review those problems. And then, but I need to press on here. So let's go ahead and press on here. With chapters 8 and chapters 9, I'm going to combine and take a look at that. Let's see what I want to share. I'm going to share 1 to 52. Okay. All right. Chapters 8 and 9 are chemical reactions, and so when we do that, we think about evidence for chemical change. So let's take a look at some of these. This is going to deviate from the book. My nomenclature deviated from the book too, but I'm going to deviate from the book's presentation for this. And so make sure the notes make sense to you. All right. Grab some PowerPoints. All right. Here's a chemical reaction here. This is space shuttle. This is a rocket here. And this is hydrogen and oxygen, the reaction between hydrogen and oxygen. And they're using liquid, liquid oxygen, liquid hydrogen. It's going to make this thrust here. This is another chemical reaction here. You can see the color change. Sometimes color changes, but what we're going to see is the color is going to fade with time. So there's definitely something happening here. So let's say this is initial after 2 seconds, after 15 seconds, after 41 seconds. So definitely something happened there. There's a chemical reaction that happened. This is also a chemical reaction that occurred here, So this one, if we look at this, obviously something's happening here. There's a lot of heat, a lot of energy, sound, a lot of light being given off. Here's the colors changing.
Professor, we don't see anything.
Okay, sorry, you guys can't see it. Okay. Let me, I'm sharing the wrong screen, that's why. Okay, can you guys see it now?
Yes.
Okay, thanks. Yeah, my speaker's not working for some reason. All right, here I was talking about chemical reactions. Obviously, chemical reactions happening here. There's some chemical reactions. There's fuel and oxidizer. The fuel is hydrogen, the oxidizer is oxygen. And so this reaction is just simply the reaction of hydrogen and oxygen. And it gives off a lot of energy. And so let's take a look here. So we have hydrogen, H2. Hydrogen, it can be in different forms. When they have it here, they try to liquefy it because if you have hydrogen gas, it's a lot of empty space. And so this is the reaction between liquid hydrogen and liquid oxygen. We need 2 hydrogens for every oxygen. This is a high energy mixture. And then when this reacts, it's going to form 2 H2Os. The H2Os in this case, we can go as gas because that's going to provide the volume and the thrust for this to happen. So this is a very energetic reaction. And so we could just write this in a standard way, which would be this: 2 hydrogens, liquid in the space shuttle, plus an oxygen liquid is going to give us 2 H2O gas. Liquids don't occupy much space, but gases do occupy a lot more space. So the volume expands, giving it thrust. It can go up. That's pretty impressive. Here's what I was talking about, the color fading. So here's the initial color, let's say, and then after 2 seconds, after 15 seconds, after 41 seconds, colors disappeared or close to it disappearing. It's still there, it's faint, but there's some kind of reaction going on. Color change like that, indicative. This is where you're adding a drop of liquid to another liquid, and when that drop hits, it makes this cloud. This cloud is actually tiny crystals, and this is called precipitation. Precipitation is when we start to form a solid. Eventually the solid will settle to the bottom of the test tube, but these tiny crystals could be suspended, you know, for some time in the liquid here. But this cloudy thing is called a precipitate. And so that's chemical reactions occurred there. Here's another chemical reaction. You can see bubbles of gas form. And so let me write this down. You know, this one's oops. We're called precipitation. And precipitation is formation of a solid. And precipitation, people usually just write precipitate, PPT, and the solid, people usually refer to that as the PPT, the precipitate, is the solid. This is when we have bubbles of gas form. This is called effervescence, you know, effervescence. Gas formation, effervescence. Effervescence. Effervescence is sometimes just read EFF. Effervescence. This is a colorless gas, a clear colorless gas. This is probably CO2. It's being formed. This is energy, light, heat being generated. Chemical reaction. This is light being generated. This is a chemical reaction. Sometimes, you know, things get cold, things get hot. This could be a chemical or a physical process. But it could be an indication that chemical reactions occurred if this gets cold. Usually cold, it's taking heat away from the surroundings. And so usually for these types of things, we start off at lower energy and then it sucks heat away to go up to higher energy. This is endothermic, we say, endothermic. Exothermic processes get hot. Exothermic are the opposite. Exothermic would be a hot pad. And so if we start off at high energy and drop to low energy, it's exothermic. If we start off at low energy and go up to high energy, it's endothermic. This is a cold compress, so it's got to be endothermic in this particular process. This is the reaction of sodium metal with water. Here, sodium metal with water. You saw the explosions at Lake Lenoir in Washington. Those explosions are because when sodium metal reacts with water, it forms hydrogen gas. And if the hydrogen gas gets hot enough, it'll explode with air. In this case, it just didn't get quite hot enough to explode there, but it could easily. Color also changed because they put some kind of indicator in here. Otherwise, color wouldn't change. The indicator changes color depending on the response that it undergoes. A candle's obviously a chemical reaction here. This is just light energy. This is light being separated into the colors here by a prism, the red and then violet. It spreads out because different wavelengths of light travel at different speeds through the prism. So evidence of a chemical change, color change, formation of a solid, which we call precipitation, formation of gas, which we called effervescence, absorption and release of energy, which we called Absorption is endothermic, release of energy is exothermic, or emission of light. Different colors of light be emitted, including non-visible light like infrared or ultraviolet or whatever. These are the states that we use, solid, liquid, gas, aqueous. Aqueous just means dissolved in water. Then we can write these as chemical reactions like this. This is methane combustion. Methane combustion, we have a molecule of methane reacting with a molecule of O2. Actually, this is not balanced here because we have one carbon. We have 4 hydrogens. You can't see the hydrogen. There's 1 hydrogen on the other side of this. There's 4 hydrogens. We only have 2 hydrogens here. And so the atoms aren't quite balanced, and we have 3 oxygens here, and we only have 2 oxygens here, so we need to balance this. Now, this is the way we balance it. In terms of balancing it, we could have 2 oxygen molecules instead, and then we end up with 2 water molecules here. Now all the atoms are balanced. 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens, 4 oxygens. So everything's balanced. And just the atoms just got rearranged here. So that's it. We can either think in terms of individual molecules, or we can think in terms of moles of molecules. 1 mole of methane, 2 moles, 1 mole, 2 moles. Here's the space shuttle reaction, hydrogen with oxygen. To properly balance, we need 2 hydrogens for every oxygen. We're going to make 2 H2Os. Rather than using moles, we could use dozens, but dozens you can't see. It's not macroscopic. So if we use dozens, it's not very effective. What's much more effective is 2 moles. 2 moles is a big quantity, and 1 mole is a big quantity. So we can see that. And so 1 mole of hydrogen plus 1 mole of oxygen would yield 2 moles of water. Dozens not very practical. Hydrogen and oxygen is always a violent reaction here. It's an unstable mixture. It's got high chemical potential energy. Let's see here. This is a balloon, the Hindenburg, filled with hydrogen. Unfortunately, hydrogen and oxygen aren't stable, and if it catches on fire, it's in trouble. And so that's what happened. Okay, this one, what is going on here? Okay, this is actually sodium peroxide on here. Sodium peroxide is used to bleach animal, vegetable fibers, feathers, bones. It's a bleaching agent, sodium peroxide. Yeah. And so, sodium, what's the formula for sodium peroxide? Put that out. Na2O2. So, it's coal, charcoal. Carbon, charcoal is amorphous carbon. You burn it to form CO2. It's hard to burn carbon though. Here's some reaction A reacting with X to form AX. This is one we saw earlier, mercury 2 oxide decomposing. Lavoisier. This is the reverse. So this is a synthesis, or what we call a combination type reaction, where we're combining to form AX. But you can take AX and decompose it back into the elements. So we can take a compound and decompose it into elements using chemical means. In this case, heat to break it apart. Sometimes we don't use heat to break things apart. Sometimes we use electricity to break things apart. And so I showed this earlier, the electrolysis with 9-volt battery. So you take H2O, you could break it apart into the elements, hydrogen and oxygen, by passing electric current through there, right number of volts. This is what I talked about in the Roman times. You know, Romans made calcium oxide by burning calcium carbonate, you know, from calcium oxide, from CO2. So back in the Roman days, they have these kilns still set up. I don't think they had railroad cars, though. And some of those kilns are still standing. This requires temperatures between 825 to 1,000 degrees Celsius. Calcium oxide is one of the most widely used chemicals in the world, you know, because of course, because of concrete. That's why concrete is all over. What's this supposed to show? Let's see, I'm reading the caption here. This is just showing a horse running. I guess this will make sense when we look at the next slide. When we look at the next slide, this is showing chemical reaction, reacting, you know, I think. Yeah, some chemical reaction, reacting over time. So just like this, we can follow, this is called a reaction progress. If we follow a reaction from the start to the end and take little snapshots, that's called reaction progress. Eventually we get to the products. This is professor at Caltech, Professor Zawal, who leads a team of scientists who study the behavior of matter at a time scale. So this person studies chemical reactions, and, you know, as they're occurring. When chemical reactions occur, how do the atoms rearrange? How the atoms rearrange is that, you know, when we have bonds, these bonds have to be broken and new bonds have to be formed. And so we have all this action going on. So this person studies it at very fast time scales. And so when you look at the stopwatch here, it's at femtosecond time scales. So we're looking at 1 femtosecond later. Well, what is a femtosecond? A picosecond is 10 to the minus 12, so a femtosecond is 10 to the minus 15. And so 10 to the minus 15, what's that? Well, what that is this. If you take 1 second and divide it by 1,000 trillion slices, one of those is a femtosecond. And so take 1 second and divide it into 1,000 trillion pieces, and that one piece would be a femtosecond. That's how fast this is taking snapshots. Picoseconds is too slow. You know, some of these reactions, 1 picosecond later, it's already done. You missed all the action, you know. Here, they're pouring water, dripping water. This is burette, by the way. They're dripping water from the burette onto sodium. Sodium is very reactive. It's a powerful reducer. Water is a very weak oxidizer, but we get a violent reaction here. And this violent reaction is going to form sodium hydroxide, sodium here, and hydroxide here. The sodium ions are actually encapsulated by water molecules, and the hydroxide as well. These are called hydration spheres, you know, how the water molecules encapsulate that. And hydrogen. The hydrogen gas is what's igniting here, hydrogen and air. That's what we have here. When we have sodium hydroxide dissolved in water, it's actually split apart like this into what we call hydrated or solvated ions. What's this slide showing? This slide is showing calcium metal reacting with hydrochloric acid. You know, this is effervescing. This is making hydrogen gas here. Well, looks like a different. Here's where we're taking an element plus a compound. It's making a new compound and a new element. This is called a single replacement type reaction. This will be an example here. Copper dipped in silver nitrate here. This fuzz on here are silver crystals. Copper is being eaten away. When copper 2 ions are dissolved in water, it makes a blue color like this. Look at these. This one's called a double replacement reaction. And where we got a compound and another compound yields 2 new compounds. This precipitation is an example of a double replacement reaction here. This is a precipitation. These are the patterns that we see. They, just to summarize, they had a combination where we combined 2 elements to make a compound. They had a decomposition where they took a compound and decomposed it into 2 elements. They had single replacement like this, where we took an element A plus a compound BX and formed a new compound AX and the element B. This is a double replacement. We're taking compound AX plus BY and form 2 new compounds, AY and BX. Here's some abbreviations. I'm going to deviate, though, from your book's presentation. This is not a double replacement reaction. It doesn't fit any of these categories, this reaction. This is carbon monoxide and water. Yields carbon dioxide and hydrogen gas. This is a very important reaction. This is steam, actually. So carbon monoxide plus steam yields carbon dioxide plus hydrogen gas. It's used to generate hydrogen gas. It's this one. Some more reactions here. Yeah, definitely some reactions occurring there. This looks like bromine vapor. Bromine. This is P4, and there's chlorine gas being dispensed by this little glass nozzle or pipette. When the chlorine hits the phosphorus, boom, we get a violent reaction. It's an example of redox reaction. There's some more reactions. Actually, I don't know what that one is. I'd have to look it up. Oh, am I going to put these slides up on Piazza? Yeah, I'll put these slides up on Piazza. This is just pictures of reactions. We'll look at more reactions as well. Okay. All right, so most of this is just going to be by notes, and so let me talk about it. No, 45. Okay, I'm going to stop sharing that screen, and then let's go back to the whiteboard that I had up earlier. So let me share that. Okay. I can go back to the whiteboard. Just 1 second. Oh, yeah. Okay. Okay, let me mute here. Okay, well, actually, let's take our break now. So we'll take our 15-minute break, and then we'll be back again at 2:01. Okay, thanks. Okay, I'm back. We'll get started again. Oops, I forgot to pause the recording. There's going to be a long gap in the recording for the break. But let me stop this recording.